All right. It's a pleasure to be here. I was sitting with Hiranya when I sent in the talk title, and she encouraged me to give a big picture talk. So my title essentially encompasses everything I've worked on for the last 25 years. I'll try to fit it into 25 minutes. So I'm going to try to do two big picture things in this talk. One is to really give the big picture of what I have learned about the connection between the bright side of the universe and the dark side of the universe in that time, and also a little bit about what I'm most excited about for the future. So as we just heard in the last talk, this model has actually persisted for more than half of the IOA's lifetime, and mine. I'm approximately the same age as the IOA. Although I learned this is actually more than the 50th anniversary, according to the webpage. So in this model, we have a few basic things that we think are part of this model. We have a theory of gravity described by general relativity. We have an idea of how the initial conditions in this model were formed. We have an idea of what most of the matter is. And we have an idea of what the energy density is dominated by. So where are we with that? So far, GR seems to work everywhere it's been tested. In terms of inflation, I think we have really strong circumstantial evidence that this is the right picture, including that the universe is flat and we have Gaussian adiabatic fluctuations and we have a tilt, which is close to but not exactly 1. We're currently ruling out interesting models. I would say still this evidence is circumstantial and we'd like to actually detect this. In terms of dark matter, the favored idea is that it's non-baryonic and at least close to cold. And I would agree with Carlos that this is consistent with data over a very wide range of scales. But of course, all of the direct searches we've done for the dark matter particle have come up empty. And in terms of the energy density, it is mostly consistent with being constant. As you've heard this week, there are maybe hints of otherwise. I would definitely personally label those as hints at this stage. And, we still don't understand why dark energy should have this constant value or any other value. But a few things have changed over the last 25 years. So the first is we have really understood how structure formation works in this class of lambda CDM-like models in a lot of detail, right? Over a wide range of scales for a wide range of cosmological parameter space, and increasingly for a variety of alternative models for what the dark matter might be. And this has been a really massive, almost 40-year endeavor using the largest supercomputers that we have available. And as we also just heard, this model, and we're just going to stick with lambda CDM-like, right? Things that are close to lambda CDM but may have small variations. It really makes a very wide range of predictions. The numbers of dark matter halos, the clustering of those halos, features in the matter clustering, the galaxy clustering, hierarchical merging, lots of substructures and destroyed substructures. And we can test these predictions on a very wide range of scales. And many of these basic predictions were actually established 20 to 25 years ago, shortly after we could really do the computations. But they've recently really reached a new level of precision. And these predictions are really well tested on large scales, and they seem to hold up. They are much less well tested on small scales, where both the modeling and the data are still catching up. On large scales, we can now make very precise predictions, and there's a whole industry of people doing large cosmological simulations over a wide range of models. And this has now led to people being able to make predictions for the statistics of many things, the matter clustering, and then things that depend on that, at essentially the percent level for the full range of cosmological parameter space that we are interested in. And this is a huge advance. I mean, this was really not true 10 years ago. So I just want to emphasize that this has been a really big effort of many people in the community. And those emulators now span, a wide range of things that we might care about, all the way from the Lyman alpha forest to the details of galaxy clustering. Now, of course, the actual nature of dark matter does impact these predictions. And if dark matter is close to cold, but not precisely cold, then it might do something a little bit different. It might look identical on large scales, but different on small scales, and that could result in, for example, fewer substructures, different density profiles, etc. And there are many models that look just like CDM on large scales, but differ on small scales. Those include warm dark matter, ultralight dark matter, self-interacting dark matter that has interactions with the standard model, dark matter that has late time decays. All of these can lead to differences in the predictions of small scale structure. Okay, so first thing is the predictions. Second is that we've really mapped the universe at increasing precision, and this has been an even larger effort, a 50-year endeavor essentially, that has used purpose-built instruments. I think we heard from George earlier that this is we're entering the peak spend era, where we have multiple billion-dollar experiments on the ground and in space. And just to give a sense of how rapid this progress has been, this is sort of approximately in the first column, the 25 year ago version, and in the middle column, the current model. This is incomplete and biased version of this plot, but just to give a sense, we now are at the 30 million galaxy spectra, 300 million galaxy images, soon to be much more with LSST and space-based surveys. We've now gone to the high redshift frontier around redshift 14. I'm very excited about the future where we can really do statistics at that high redshift era. We've detected in the last 10 years 3 times as many galaxies in the Milky Way, and I expect this to at least double again in the next 5 years with LSST and other surveys. And of course, Gaia has provided a revolution in astrometry. And these maps are just beautiful, and I won't spend a lot of time on this recent DESI result, but mapping the universe in 3D with 30 million galaxies is a phenomenal achievement. And I have to say, just my favorite thing about this map is just, after 25 years of making models like this in our simulations, to actually see this map in the universe, in the sky, is to me just totally amazing. And I think we shouldn't discount, the achievement that we've done as a field to be able to make these predictions and measurements at this level of precision. So a third piece of this puzzle is the way to connect the predictions and the measurements. And I think I've been very excited about this new suite of tools that have developed over the last 2 decades or so to connect these two things. And this includes, very physical models here on the left-hand side, where we try to put in all of the physics we understand and calculate it from first principles, to these models on the right-hand side that are much more data-driven, that take some assumptions about what's happening with the physics, but also really try to use all of the data as constraints and to inform our understanding of how the galaxies and dark matter evolve together. And this field has sort of become known, the galaxy halo connection. This is an interesting little bit of history. The first paper that had galaxy halo connection in the title actually referred to something completely different. It was the relationship of galaxies to, it was a relationship of the galaxy, the Milky Way, to its stellar halo. There was a nice review article on that topic, which is completely different, in 1996 by Cindy Vandenberg. And then the next one within in the title is from me in 2008. But you can see that there's been a huge jump in this. But this set of things that we have learned, so this plot shows the fraction of mass in stars as a function of halo mass. And this is in the local universe with a whole bunch of different ways to constrain this. And the takeaway here is that galaxy formation is not very efficient at any mass, and the efficiency peaks at a few percent, roughly at the mass of the Milky Way, and it's more or less efficient at higher and lower mass because of various feedback processes. And this is really something that we had ideas about from the models, but was really driven by the improvements in our understanding of the data and how to put that data together in the context of the predictions of lambda CDM halos. And just to give a couple of examples of what we have learned from this approach, I really think this kind of empirical modeling has helped us build a clear picture for the evolution of galaxies over time, informed by data. So one example is, this is an old plot that shows the efficiency of star formation as a function of halo mass and time, essentially putting together all of the data we have from a wide range of surveys with our understanding of how halos evolve. And we learn really useful things from this. For example, that plot I showed you in the last thing seems to persist essentially at all redshifts. Galaxy formation is the most efficient just below the mass of the Milky Way at essentially all redshifts. And in this, we're learning a lot more in this sort of regime from JWST, and I think this is very, very exciting. You heard another example from Alice yesterday. This same kind of picture tells us basic things about the formation of our own galaxy. For example, that most of the stellar halo was likely built by just a few events, because even though we expect thousands of substructures in the Milky Way, because the stellar mass-halo mass relationship is steep, only a few of those actually have a sufficient number of stars to impact the stellar halo. And a third thing is that I think over the last decade or so, this kind of empirical modeling has really become a key tool to inform more physical models, and vice versa. I think they've really worked very well together in concert to build our picture of galaxy formation. So this suite of kind of data-driven models for the co-evolution of galaxies and dark matter halos has contributed to a clear picture of the evolution of galaxies within dark matter over the full range of masses and times that the statistical populations of galaxies have been able to be observed. It has also been used to understand how we most effectively marginalize over galaxy formation physics to do cosmology. And it has also been used to understand the important interplay between galaxy formation and dark matter physics on the smallest scales that we have access to. A fourth advance that has happened over the last couple of decades is that improved modeling has really enabled us to push cosmological probes to increasingly smaller scales. And this is a very active topic of research that I won't be able to do justice to in this 1 minute, but I just want to give one example of this. A recent paper that uses DESI data as the lenses and DES data as the sources does a model that really provides beautiful constraints on sigma 8 and omega matter. And this modeling approach is using approaches like effective field theory, but combining it with simulation-based predictions for smaller scales. And that really enables us to use the smallest scales that we can trust in the data. I think there's both an opportunity and a challenge in this area. As we push these measurements to smaller scales, we really have to think very carefully about the galaxy dark matter connection or galaxy bias. And I think this is a challenge, but it's also a big opportunity. We do know things about galaxy formation, and we do if we ignore everything we know about galaxy formation, we are throwing away a huge amount of the data. But if we assume too much about what we know about galaxy formation, we almost certainly will be biased. So I think this is a really exciting area of work that is important to get the most out of the data, and it's something we're thinking about. So summarizing what I've said so far, we've understood structure formation in detail. We've mapped the universe at increasing precision. We know how to connect these things, and we can push the modeling to smaller scales. So what's next? Can we break this model? Can we find new physics? And can we better understand really the extremes of galaxy formation? So the first thing that's next is tons of data. The last few years have already been exciting, but I think the next 2 decades promise to be even more exciting in terms of the data that is coming at us. This is, again, an incomplete version of the data that's coming at us, but I think it's quite exciting. So what are we going to do with all of these data? So I'm just going to so big picture, my questions are the same as they have been since I started working in this field. How did the universe form and what it is made of? And my personal philosophy here for how to answer this question is really, how do we really combine models and data to solve the biggest questions in galaxy formation, cosmology, and dark matter jointly, together, not just ignoring one of these things and pretending we've solved it, but trying to solve these things together. And in the coming era, I think this really is going to mean thinking carefully about how do we build the right kinds of models to keep up with the data. I think we're already behind. We're already not using the data that we have, and we have a lot of work to do to keep up and so that our methodology can keep up. So in the last few minutes, I'm going to focus mostly on this last question: what can astrophysics tell us about dark matter? I think although I was born in the church of CDM, that Carlos is a key proponent of, I'm a little bit more agnostic. And, I think one of the things that's worth remembering is that we actually have, depending on who you ask, between 90 and 50 orders of magnitude of uncertainty in what dark matter is. Most of the searches so far have been, in a very narrow range. Looking primarily at standard WIMP dark matter. But I think there's a huge range of possible ways to search for all of these dark matter models in the next decade or two. And what's exciting to me is that I think astrophysics will play an increasingly important role. There are places where astrophysics is the only way to get new information, and places where it can play a supporting role. So specifically, even if we live in a CDM-like universe, that doesn't mean we live in a perfectly CDM universe. And in fact, no, CDM is essentially a schematic model, right, that says that interactions don't impact structure formation. And even WIMP CDM has some cutoff in this power spectrum. And so we now know we're very close to CDM because this model works really well over the range we've tested, but many things can do different things on smaller scales. And so we'd really like to probe that as far down as we possibly can. So I think there's a wide range of ways we can probe small scale structure. I have personally been most focused on these top 3, dwarf galaxies, strong lensing, and stellar streams. And I think we have a bright future in all of these areas. One piece of that bright future is going to come from Rubin Observatory. So the LSST is going to map half the sky, fast and deep, make a 10-year color movie. We've just built this camera, and we're going to be hosting the data at Slack. So here's the people who sent the camera off just because they know how to hold a sign. Here's the people who actually built the camera. Here is the camera arriving at the summit and actually being installed. So this just happened 2 months ago. We're very, very excited that this is happening soon. So, the range of science that Rubin is going to do is broad, make maps of the entire southern sky, find a whole bunch of new dwarf galaxies in the Milky Way, find probably at least 100,000 strong gravitational lenses, and of course, every night, 1 million things that changed. So I'm going to spend in my last 5 minutes a little bit more on these small-scale structure probes. Rubin plus the follow-up surveys that it will do will provide really a transformative advance for each of these probes. But in order to make the most of it, we also really need to understand the galaxy halo connection in this low mass regime and its degeneracies with dark matter physics. So of course, in the last few years, we've discovered a ton more satellites in the Milky Way. And this already is able to constrain a range of models. And that's because warm dark matter or warm dark matter-like models suppress the number of observed galaxies. So just the fact of seeing these things in the Milky Way already puts strong constraints on dark matter. And I don't have time to go through this in detail, but please feel free to ask me. What we know so far is that any model that suppresses small-scale structure really can't do anything above about 10 to the 9 because we already see all of those objects. So that constrains warm dark matter, but also a range of other dark matter models. Now, CDM makes a very clear prediction that these halos should extend to very low masses, but small halos should be dark, so they should not actually have galaxies. So we'd like to push that threshold as far as we can and ideally detect the dark halos below it. And so I think two of the ways to do that, to actually detect the dark halos, are strong gravitational lensing and stellar streams. Both of them are sensitive to small dark systems. So you heard about this briefly in the last talk. Basic idea is you've got a lens here, you've got a background source, and the substructure, either in this halo or along the line of sight, can distort the images. And this is a place where AI/ML techniques and simulation-based inference have really, this is prefacing the future talk. I think this is where it actually is revolutionary rather than evolutionary. We can really do things that were not possible before. And what my group has recently shown, led by Sebastian Wagner-Carena, is that we can really use this to get unbiased estimates from 100 lenses or so. And we've done this using new kinds of simulation-based inference techniques where we really have this, where we simulate the entire image with different amounts of substructure, different kinds of source galaxies. The exciting thing here is we've actually made the simulation step as fast as the inference step. So we're really doing really great inference here. I think we still don't know what the limits of the technique are, but I am personally optimistic that we can get to 10 to the 7. The next way is looking for gaps in streams, which we just had a question about. The basic idea here is that dark halos within the Milky Way will disturb streams. We already have a lot of these streams, and we almost certainly will find more in the next few years. So I think there's two things that are needed to do this right, like there are for most probes, better models and better data. On the better data side, not only do we want to detect as many streams as we can, but we want to measure their velocities as well as we can. So in order to do that, we're starting a new spectroscopic survey, which will have high radial velocity precision. The key here is to get to 100 meter per second velocity precision so that we can actually see the impact of 10 to the 6 solar mass subhalos. So that would be a huge advance if we can get that far. Those halos are almost certainly dark, would provide clear evidence of CDM. We're planning on doing this survey all sky with Magellan and MMT, 2 new spectrographs that are now designed and we're starting to build. And we're hoping to have this on sky so that we can actually see the things that are newly detected by the Rubin Observatory. So in order to make progress on all 3 of these small-scale structure probes, we also need improved modeling. And this is something that I'm thinking a lot about. How do we do the full cosmological context? How do we understand the Milky Way versus other systems? How do we really track dark and stellar structure robustly. I think there's a lot of progress that needs to be made in this area. How do we fully understand the impact of baryons? And there's a lot of details on this slide, just to say that my group is thinking about all of these steps. Many others are as well. And so I think this combination for small scale of new methods, new data, and new models is going to be very powerful. And just to say briefly, as we think about future constraints on the galaxy halo connection, we have JWST, we have lensing, able to learn more about this regime. We have potentially detecting the limit of galaxy formation here, detecting new dwarfs here, looking at low mass galaxies at all redshifts from JWST, Roman, and Rubin, and especially with the combination of spectroscopy and lensing, really understanding the dependence of these plots on galaxy properties. So a lot of possible ways to make improvements in our understanding of this. So I will end there. Looking to the future, we have very exciting new data coming at us fast. I think we have huge potential to learn more about what the dark matter is. I think the Milky Way is a very exciting frontier. In order to get there, we need to take the modeling there as seriously as we have taken the modeling of large-scale structure in the last few decades. And we should really think hard about how we find the sweet spot in using all of the data we have. I will end by just, we just celebrated at KaiPAC our 20th anniversary last year, so I will just, as a baby institute compared to the IOA, wish you all happy 50th. Thank you.